Welcome back in this lecture of the vector integration. In my previous lecture, I have given you the proof of the Gauss Divergence Theorem. Now, in this lecture, I will solve problem based on Gauss Divergence Theorem. So, let us start with the problem. For any closed surface S, show that your curl of f dot n ds is equal to 0. So, solution. Let us apply the Gauss Divergence Theorem. So, by Gauss Divergence Theorem, your curl of f dot n ds is equal to your f dot n ds equal to divergence of f into dv. So, this is equal to divergence of this f. That means in place of f now we have curl f. So, we have divergence of curl f dot dv. Now, in my vector calculus, I have given you the proof of this divergence curl of f equal to 0. So, we have this divergence of curl f equal to 0. So, this is equal to 0. Because your divergence of curl f is equal to del cross f, and this is equal to 0. Then we have the question, evaluate r dot n ds, where S is the closed surface and your vector r is xi plus yj plus zk. So, solution, again by Gauss Divergence Theorem, we have this f dot n ds equal to, by Gauss Divergence Theorem, this f dot n ds equal to divergence f, that means divergence of r into dv. Now, as your divergence of r is 3, so this is equal to v times 3 dv. So, this is your 3 into dv. Now, this dv will be the volume of the region bounded by this closed surface, and say it is v. So, this is equal to 3 times v. So, your answer is 3v, because your divergence of r is equal to, your divergence of r means I dot del r upon del x, and your vector del r upon del x is your I. So, we have I dot I plus j dot j plus k dot k. So, it is equal to 3. Then our next question is, evaluate this surface integral where my f is equal to 2x plus 3zi minus xj plus yj plus y square plus 2zk, and S is the surface of the sphere having center at 3 minus 1 2 and radius 3. So, here we have to evaluate this double integral where your vector point function f is equal to this one, and your surface is the sphere with center 3 minus 1 2 and radius 3. So, again let us apply the Gauss Divergence Theorem. So, by Gauss Divergence Theorem, this double integral f dot n ds is equal to divergent f dv. So let us evaluate divergent f. So divergence f will be del by del x of the first component of f. So this is your 2x plus 3z plus del by del y of second component, which is your minus x and minus y. Then we have del by del z of third component, which is your y square plus 2z, and it is equal to 2. Now the differentiation with respect to y will give you minus 1, and differentiation with respect to z is 2, so this is your 3. So your divergent f is 3, so therefore your surface integral f dot n ds is equal to divergent f into dv, and your divergence f is 3, so we have 3 into the volume of the sphere, and the volume of the sphere is equal to 4 upon 3 into pi into radius cube, and here we have the radius as 3, so this will be a 3 cube. Now 1 3 will get cancelled with this one, so this is your 3 3 are 9, 3 are 27 into 4, and hence it is 108 pi. So the value of this double integral is equal to 108 pi with the help of the Gauss Divergence Theorem. Then our next problem is then evaluate the double integral a square x square plus b square y square plus c square z square power half into ds, where s is the surface of the ellipsoid, a square x square plus b square y square, ax square plus by square plus cz square equal to 1. So let us evaluate this double integral where your s is the surface of the ellipsoid, this one. Please note that this ellipsoid is not in standard form. So the standard form of the ellipsoid is x square upon x square plus y square upon b square plus z square upon c square equal to 1. So solution, again we will use the Gauss Divergence Theorem, but for that we need your vector point function f. So let us evaluate your f. So for that we need your normal vector to the surface. So let us assume the scalar point function phi at ax square plus by square plus cz square minus 1. So your grad phi will be 2axi plus 2byj plus 2czk, and your surface normal will be grad phi upon mod of grad phi, and this is equal to 2axi plus 2byj plus 2czk upon 4a square x square plus 4b square y square plus 4c square z square. So again it is equal to axi plus byj plus czk upon square root of a square x square plus b square y square plus c square z square. Please note that this is your value of f dot n. So your f dot n is this one, where your n is this one, and our f dot n is equal to a square x square plus b square y square plus c square z square whole power half. So this implies Now we need the value of f, and your vector n is axi plus byj plus czk upon a square x square plus b square y square plus c square z square equal to again square root of a square x square plus b square y square plus c square z square. So this is equal to f dot axi plus byj plus czk equal to a square x square plus b square y square plus c square z square. Now guess your f. So you can see that if you take your f as axi plus byj plus czk, only then the product of f and this vector will be equal to this one. So from here you can see that your f is equal to axi plus byj plus czk, because if you choose this f, only then this left hand side will be equal to this right hand side. Now we have the value of f, so let us guess the value of divergence f. So your divergence f will be equal to del by del x of the first component, so we have a, del by del y of the second component, so we have b, and del by del z of the third component, so we have c. Now by Gauss Divergence Theorem, your surface integral f dot n ds will be equal to divergent f into dv, and this is equal to a plus b plus c of b into dv. Okay, so this surface integral is equal to, so this surface integral is equal to a plus b plus c into b, where v is the volume of ellipsoid, where your v is the volume of the ellipsoid. Now at volume of the ellipsoid, x square upon a square plus y square upon b square plus z square upon c square equal to 1 is 4 upon 3 into pi into ABC. This is the volume of your standard ellipsoid. Now in our case we have a in place of 1 upon a square. So you can see that if you replace this, in our case we have small a in place of 1 upon a square. So you can see that your a square will be replaced by this one. So your a will be replaced by 1 upon a. So for our case, we will have our a as 1 by square root of a, b will be replaced by 1 upon square root of b, and c will be replaced by 1 upon square root of c. Now for the ellipsoid, in our case we have this ellipsoid ax square plus by square plus cz square equal to 1, or we can write it as x square upon root a square plus, we can write it as 1 upon root a whole square. Then we can write it as 1 upon root b whole square. Then we can write it as 1 upon root c whole square equal to 1. Now you can see that in place of a we have 1 by root a, in place of b we have 1 by root b, and in place of c we have 1 by root c. So your volume of this ellipsoid will be, therefore volume of ellipsoid is equal to 4 upon 3 into pi into a, means 1 upon root a into 1 upon root b into 1 upon root c. So this is equal to 4.35 square root of ABC. So this is the volume of this ellipsoid. So your surface integral is equal to this is equal to A plus B plus C into B, and it is equal to 4.3 pi into A plus B plus C divided by square root of ABC. So this is your solution of this problem. Now let us verify this Gauss Divergence Theorem with the help of a problem. So that means we will evaluate both surface integral and volume integral, and then we will say that the value of both surface integral and volume integral is equal to each other. Only then we can say that our Gauss Divergence Theorem is verified. So our question is, using Gauss Divergence Theorem, verify Gauss Divergence Theorem and show that the surface integral x cube minus yzi minus 2x square yj plus 2k and ds is equal to a power 5 upon 3. We have to verify Gauss Divergence Theorem, and further we have to show that this is equal to this value, where your S is the surface of the cube bounded by the planes x equal to 0, x equal to a, y equal to 0, y equal to a, z equal to 0, and z equal to a. So this is our surface. Okay, solution. Let us evaluate the volume integral first. Here we have to verify this f dot n ds is equal to divergence f into dv. So here we will verify that this left hand side is same as this right hand side. So first of all, let us evaluate this right hand side. For that we need divergence f. Now your divergence f will be del by del x of this first component of f, which is your 3x square. Then del f upon del y, that means we have minus 2x square. Then del by del z of the third component, which is your 0. So this is equal to x square. So therefore this right hand side is equal to, this is equal to x square, and your dv will be dx, dy, dz. Our limits are x is from 0 to a, again your y is from 0 to a, and your z is from 0 to a. X square, dx, dy, dz. Now if you integrate x square, then this will be your x cube upon 3. So on putting x equal to 0 to a, we will have a cube upon 3, and then the limits of y from 0 to a and z from 0 to a, dy, dz. Now the indication of dy will be y, and hence it will give you a. Again, one a will be from here, so this is equal to a power 5 upon 3. So your right hand side is a power 5 upon 3. So if you have to evaluate just the value of this integral, then this is your solution. But now here we have to verify Gauss Divergence Theorem. So now we will evaluate this left hand side, which is your surface integral. So we have the square. So this is your say y-axis, say this is your x-axis, and say this is your z-axis. This is your A, B, C, D. Say this is your origin. This will be your E, F, and then we have G. Okay. This is your A, 0, 0. Here we have B, 0, 0, 0, B, 0. And here we will have 0, 0, C. This will be your 0, B, 0. And here we will have A, 0, 0. Now, our surface integral will be the sum of 6 surface integral for each surface. So, in our case, this surface integral S f dot n ds will be the sum of, for the first part, A, B, C, D, f dot n ds. Then we will evaluate the surface integral for this part, O, E, F, G. Then we will evaluate the surface integral for this C, B, E, F. C, B, E, F. And then your f dot n ds. Then its opposite. We have O, A, D, G. Then we have this part, O, A, B, E. Then its upper part will be your D, C, F, G. So this is equation number 1. So now we have these 6 integrals, 1, 2, 3, 4, 5, 6. Now let us evaluate these 6 integrals one by one, and this sum should be equal to a power 5 upon 3. Now the unit normal for this part OABE will be your this OABE. This is in xy plane, so its unit normal will be minus k. This outer normal will be minus k. Then this is your CBEF. For this we have the unit normal as J, and its opposite is this AOGD. For here we have the unit normal as minus J. For this part DCFG, our unit normal will be K. And now for this part ABCD, your unit normal will be I. And for this part OEFG, your unit normal will be minus I. So we have these unit normal. Now just evaluate the values of these 6 integrals. These 6 integrals. So the first integral is ABCD f dot n ds. Now for this ABCD, our outward normal is plus I. So this will be your f dot I. Now the value of f dot I is equal to x cube minus yz. This f dot I is equal to, this is your f dot I, and here we can write this as, and where your x is a. Now for this part A, B, C, D, our x is a. So this is your x equal to a. So we can write x as a. So this is your a cube. Then we have dy dz, and you can see that the value of y in this case is from 0 to a, and your z is again from 0 to a. So this is your 0 to a cube minus yz dy dz. So if you evaluate, if you integrate with respect to z, then this will be your a cube z. So we will have a4, and this will be your z square by 2, then this will be your a square by 2 into y. Now the integration with respect to y. Again this will be your a square by 2, and the integration of a power 4 will be your a power 4 into y, so we have a power 5. Now this will be your y square by 2, so this will be your a power 4.4. So this is the value of first integral. Then this is your ABCD. Then your OEFG, f dot n ds is equal to OEFG. Now for this part, your n is equal to minus I, your outward normal is minus I, and again your x will be from 0 to a, and your x is your, in this case for f dot n ds, you can say that this is your OEFG. This is in your yz plane. So for that we have x equal to 0. Now as your x is 0, so your dx will be 0, and your outward normal is minus I, so this is equal to f dot minus I. OEFG, this is your f dot minus I into ds. Now here we have x equal to a. Now here your f dot I will be x cube minus yz. Now this I dot I will give you 1, so we have OEFG yz into ds. ds is dy dz because your x is equal to 0. Please note that for this part OEFG, this portion is in yz plane, and for that we have x equal to 0. Now the integration is from y equal to 0 to a and z equal to 0 to a, yz into dy dz. Now the integration of y will be y square by 2, integration of z will be z square by 2, so this is your a power 4.4. So this is your second integral. Now let us evaluate CBEF. So the integral CBEF f dot n ds. Now CBEF, this is your CBEF. For this your outer normal is j, and for here, for this part our y will be b. So your n dot f dot n will be, in this case our n is j. In this case our n is j, and this f dot j will give you minus 2x square y. So this will be minus 2x square y into ds. Please note that for this part CBEF, your CBEF, we have y equal to b. So just put y equal to b here. So if you put y equal to b, then we have minus 2b outside, and then this is in your yz plane, so we have xz plane, so we have x equal to 0 to a, and your z equal to 0 to a, x square dx dz. Now the integration of x square will be x cube by 3, integration of z will be your dz will be your, so z. So here we have x cube upon 3, so that means a cube upon 3 into a, so a power 4 upon 3. So this is your QB a power 4 upon 3. So this is integral CBEF. Now the fourth integral is your OADG f dot n ds. Now for this OADG, this is your OADG. Again this is in your xz plane. So for this we have y equal to 0. Now as y equal to 0 and your outer normal is minus j, so you can see that your f dot n will give you minus 2x square y, and your as y is 0, so this will be your equal to 0. So this is your OADG. Now f dot n is your j, n is your minus j, so this will give you plus 2x square y. 2x square y, then we have ds. Now for this part OADG, your y is 0, so this is equal to 0 because your y is equal to 0. So we have evaluated 4 integrals. Now the fifth integral. The fifth integral is this one. OABE. Now this part, this double integral OABE f dot n ds is equal to, for this part OBEE, OAB, we have n equal to minus k, so this will be just minus 2. So this is your minus 2 OABE, because in our case your unit normal is minus k, so we have f minus dot k, and that will give you minus 2 into ds. Now again, in this case we are in this xy plane, so this will be your minus 2 into 0 to a dx into dy. Now this will be your a, integration of dx will be your a, again integration of dy will be your a, so this is your minus 2a square. Now the last integral, which is your dcfg, f dot n ds. Now this double integral, for this double integral we have n equal to k, and as our n is equal to k, and you can say that in this case our z equal to c, your n is k and z equal to c, so your f dot n will be 2 times, so this will be your, again, as your f is, as your n is equal to k, so here we will have plus 2, then integrate dcfg into ds. Again this will be your 2 times 0 to a dy dt, dx dy. This is in your z is equal to c, so this is your dx into dy. So this is equal to, again, 2a square. So now we have evaluated all the 6 integrals. Now just put the values of all these 6 integrals here. Then you can say that this right hand side will be equal to this left hand side. So if you put all these 6 interval, let us put all these 6 integrals in equation number 1. So by 1 we have the surface integral f dot n ds equal to, your first integral was a power 5 minus a power 4 upon 4. Your second integral was a power 4 upon 4. Your third integral is this one. This is your, as we have squared, so all a, b, c are equal to each other, so this is your 2a, so this will be your a power 5. Your third integral is minus 2 a power 5 upon 3. Your fourth one is 0, fifth one is minus 2a square, and your sixth one is plus 2a square. So you can see that this is cancelled, this one is cancelled, so we have 3 power here into a power 5 minus 2 into a power 5, so this will be your 2.3, 3 minus 2, so this will be your a power 5 upon 3. So now our surface integral is same as volume integral, therefore Gauss Divergence Theorem is verified. So our Gauss Divergence Theorem is verified. Now next question is, again verify Gauss Divergence Theorem. Again we have to verify Gauss Divergence Theorem for f equal to 4xi minus 2i square j plus z square k, where S is the region bounded by this x square plus y square equal to 4 and z equal to 0 to z equal to 3, where your surface is bounded by this cylinder from z equal to 0 to z equal to 3. So solution, again, here we will emulate our surface integral and volume integral. So let us draw this surface. So we have okay, say this is your y axis, so this is your z axis, and here we have x equal to x axis. Now if you take the elementary area, say this elementary area, then we have this line, again we have this portion, then we have this portion, then this one. So you can see that so again we have the rectangle, which is your, say this is your parallel to x axis, and then we have the portion parallel to y axis. So the projection of this plane in the xy plane will be your r, and here our area will be dx into dy. Now this is your z equal to 0 plane, and this is your z equal to 3 plane, and for some point of this plane our volume will be, the elementary area will be your dx into dy into dz. So now we have to evaluate this double integral, or we have to verify this Gauss Divergence Theorem for this vector point function. So for that we need the surface integral as well as the volume integral. Now, so this we have to evaluate the volume integral. So the volume integral will be solution to verify Gauss Divergence Theorem. We show that our surface integral is equal to the volume integral. Now let us evaluate the volume integral first. So our divergent f will be equal to, divergent f means del by del x of the first component. So we have 4 minus del plus del by del y of the second component. So it is your minus 4y. Then plus del by del z of third component. So this will be your 2z square, 2z. So this is your divergent f. So therefore this triple integral will be equal to, this is your 4 minus 4y plus 2z into dx dy dz. Now you can see that your z is varying from 0 to 3. Now for this circle you can say that your here your x will be from, at this point this is your circle x square plus y square equal to 4. So we have x equal to from minus 2 to plus 2, and your y will be from, if you take the strip, particular strip, then your y will be from minus 2 on root 2 4 minus x square to plus 4 minus x square. So this is equal to, x equal to will be, your x will be from 0 to, your x will be from minus 2 to plus 2, your y will be from minus 4 minus x square to 4 minus x square, and your z will be from 0 to 3. And we have 4 minus 4y plus 2z dx dy dt. So this is equal to, now if you integrate with respect to z, then we will have 3 from here, and this will be on z square by 2. So this is equal to now in the bracket we will have 4z minus 4yz, so this will be 12 minus 12y. Then we have the integration of z as z square by 2, so this 2 will get cancelled. So this is your 9. And then integration with respect to y. Now the integration with respect to y will give you, now this is your 12 minus plus 9 will be equal to, this is your 9, and here we have 12. So this is your 21 into y, then we have minus 12 y square by 2. So this is your 6y square. Then your y will from minus 4 minus x square to 4 minus x square. Now this is equal to, and then integration with respect to x. So we have x equal to minus 2 to plus 2. Now you can see that this term will be your 0, because for both the part our lower limit and upper limit will be 0. Now for this part, this will be equal to, for the upper limit this will be minus 4 square root of 4 minus x square, and for lower part this will be plus 4 minus x square. So this is your 42, and then 4 minus x square into dx. Now this is your even function, so we can write it as 2 times. So this is your 84, then we have x equal to 0 to 4 minus x square and dx. Now just use the formula, and it is equal to x upon 2, then a square minus x square. So we have 4 minus x square, then a square upon 2 sine inverse x upon a, and then we have the limit from x equal to 0 to 2. Now this will be 0 for both lower and upper limit, and for the upper limit this will be your sine inverse 1, this is your 2. Here we have 2. So now for the upper limit this is your sine inverse 1, which is your pi by 2. So we will just get pi from here. So this is equal to 84 pi. So the volume integral is equal to 84 into pi. So this right hand side is 84 into pi. Now we will show that this left hand side is also 84 into pi. Now for the surface region, again, now your surface integral is combination of 3 portions. It is your surface integral is a combination of 3 portions. One is this circular path for z equal to 0. The another is the circular path for z equal to 3, and then this circular path. Now your S1 is equal to surface integral for z equal to 3, for z equal to 0. Say S2 is surface integral for z equal to 3, and so your S3 is curved surface of the cylinder which is your given by x square plus y square equal to 4, z equal to 0 to z equal to 3. Now we have 3 surface integral, therefore your integral f dot n ds is equal to S1 plus S2 plus again S3. Now let us evaluate S1, S2, S3. Now for S1, your z equal to 0. Now for S1. Now for your S1, your n will be minus k. So therefore, your S1 f dot n ds will be equal to, and n will be minus k, and for this part we have z equal to 0. Now your f dot n will be, as our n is minus k, so this will be your minus z square. So this is equal to minus z square ds. As our z is 0, so we have S1 equal to 0. Now for this surface S3, for S3, before that let us evaluate for S2. Now for S2 we have z equal to 3 and n equal to plus k. So therefore this integral f dot n ds will be equal to, now this will be your S2. Okay, this is your, now your f is, your n is k, so this will be your f dot k, and your f dot k will be your z square, so we have z square into ds. Now your z square is 9, so we have 9, and the surface area of S2. Now your S2 is a circle, and the area of the circle will be pi into r square, so we have 36 pi. So the surface integral S2 is equal to 36 into pi. Now we will evaluate the integral S3, which is your curved surface of the cylinder given by this equation. Now for that we need your unit normal. Now this unit normal to this curved surface will be equal to grad phi upon mod of grad phi. So your phi is x square plus y square minus 4. Your n cap will be grad phi upon modulus of grad phi. So this is equal to 2xi plus 2yj upon the square root of 4x square plus 4y square, and again this 4x square, this x square plus y square equal to 4, so this will be 16. So we have xi plus yj divided by 2. So we have n. Now let us evaluate. Therefore this integral S3 f dot n ds will be equal to S3. Now your f dot n is equal to, we have 4x square minus 2y square divided by 2. So this will be equal to 4x square minus 2y square divided by 2 into ds. So this is equal to your S3 2x square minus y square into ds. Now as we have the circle x square plus y square equal to 4, so let us use the parametric coordinates. So for that, now we will use the change of variable method. So now in this case, let x equal to r cos theta, your r is 2, so we have x equal to 2 cos theta, y equal to 2 sin theta. So your dx into dy will be r times d theta into dz. Your r is 2, so this will be your, we know that in polar coordinates our dx into dy is r dr d theta. So in our case this will be equal to 2 times d theta into dz. So if you put the values of, now as we have to take the whole circle, so our theta will vary from 0 to 2 pi, and your z is from 0 to 3. So this surface integral S3 f dot n ds is equal to your theta, your z will be from 0 to 3, your theta will be from 0 to 2 pi, and this is your 2 into x square. So this will be x square will be 4 into 2, so this will be 8 cos square theta. Then we have minus this is your y square. So this is your 2y cube. We have one y here, so this will be your 4 into 2 into y cube. So this is your y cube. So this is your y cube. Now your y cube will be minus 8 sin cube theta, and then we have d theta into dz. The integration of z will be 3, so we have 3. Then your theta from 0 to 2 pi. Now you can take 8 also outside, so this will be 24. Then you have cos square theta minus sin cube theta into d theta. Now just apply the formula for sin cube theta and cos square theta, then we can say that after evaluation this integral will be equal to 48 pi. So I am not going in the details, so you can easily get the value of this. Just apply the sin 3 theta formula and cos 2 theta formula, then you can say that this bracket is equal to 2, so we 2 pi, and so this is your 48 pi. Now the sum of all these three integrals will be equal to, therefore this surface integral is equal to your S1 was I think 36 pi, yes, or your S1 was I think 0, your S2 was 36 pi, and your S3 is 48 pi, and again this is equal to 84 pi. So our surface integral is again same as your volume integral, so we can say that our Gauss Divergence Theorem is verified.